So today we'll be going over how to utilize the concepts that we've previously learned in the videos when it comes to moments and forces acting on a body. And we're going to be doing nothing but problems here to utilize those concepts to get a better idea of how to apply it. So for this example, the problem statement is determine the moment about point B of each of the three forces acting on the beam. So as you can see, we have a beam here, we have point A, and this is point B. And we have three forces that are being acted on this beam. We have force 1 equal to 375 pounds going downward. Force 2 is 500 pounds at a slope here. We have F3 being 160 pounds, 30-degree angle with respect to the vertical axis, and we have all the dimensions here at what locations are these forces being applied to. So now we see that the moments are going to be with respect to point O. So we solve what moment will the force F1, what moment will it cause about point B? What moment will the force 2, what moment will it cause along point B as well as the force 3 here? So let's go ahead and solve for the first one, F1. So let's go ahead and do the moment at point B. So this is how I'm going to be writing the moment with respect to point B being caused by force F1 here. So we're going to designate the sign convention, in this case, counterclockwise is going to be positive. So in this case, when this force being applied, it's being applied about 11 feet away from point B, and it would cause rotation along point B in the counterclockwise direction as you see here. So let's go ahead and solve for it. So the moment is equal to a force times the distance that's perpendicular to that force. In this case, is just, since it's along the vertical axis, this is already perpendicular to this beam. So it's 6 plus 5, so it's 375 pounds of force times 11 feet, which is 4,125 pound-feet is the moment being caused by force 1. Now for force 2. The moment caused by force 2 with respect to the B is equal to the force times the distance that's perpendicular to that force. But keep in mind, this force is at an angle. So we have the Y component of that, and we also have a X component. Now the X component, if you could imagine here, is basically just pulling along this point. It's not going to cause any rotation. So the X component of force 2 is not going to cause a moment, only the Y component. So we're only going to be considering the Y component, and this will be perpendicular along the axis of point B here. So this would be the perpendicular distance with respect to that point. So it's going to be 500 pounds force times 4/5 because we're only considering the y component of that force. So if you used in this case sine theta, in this case we can solve for the angle theta, but you don't have to. We could just use the opposite over hypotenuse. So 4 over 5 times the distance that's perpendicular, which is 5 feet, which gives us a moment of 2,000 pound-feet. Now let's go ahead and solve for the final force, F3. So for the third force, we have 160 pounds, but in this case, we also have an X component and a Y. Now, since the Y component is being directed right directly where point B is, this force will not cause any rotation about point B, only the X component in this case. This will cause rotation, which will be counterclockwise with respect to the B. So it's 160 pounds times sine 30 degrees. In this case, we do have the angle, and we just get the X component, sine 30 times the perpendicular distance from that X component of the force, which is 0.5 feet. So the moment that the force F3 causes along point B is 40 pound-feet. So each force causes a moment about point B. And if you want to get the resultant moment about that point, you just add them all up. In this case, since they are all positive. Now, if for whatever reason, one moment caused, a force caused a moment that was clockwise, then in this case, it will be a negative moment, and you would still add up all the moments and get your resultant moment. So let's go on and do a second problem. Now, for this problem, we actually have a crane here and we have a hook at point A. So the problem statement is the tow line exerts a force of P being equal to 4 kilonewton at the end of the 20-meter long crane boom. If theta is equal to 30 degrees, determine the placement x of the hook at A so that this force P creates a maximum moment about point O. What is this moment? So first we have to determine, okay, at what x will this P 4 kilonewtons, at what x will it have the maximum moment at point O? So the first thing is the main concept of the moment is, so the moment about point O is equal to a force times the distance that's perpendicular to this force. So how do you maximize the moment? So one way to maximize is either by increasing the force, or you could increase the distance that's perpendicular to that force. But in this case, let's say if P was at an angle, that means we would have to use sine or cosine theta to implement on the to get the force in the either the x or y component, depending which one causes a moment, and it will further reduce the moment. Instead of being 4 kilonewtons, it's going to be 4 times sine theta or whatever angle that may be, so it's going to reduce it. So we know we can't change the distance that's perpendicular because it's fixed at 20 meters, as you can see here. But what we can do is to maximize the moment is to keep this angle at 90 degrees. This is where it will maximize the moment because we won't have to split up this 4 kilonewtons into its x and y component, and only one of them will be causing a moment. In this case, we want the full 4 kilonewtons to produce a moment. So it needs to be perpendicular to this 20 meters, which is the distance that's perpendicular from P to point O. So now from here, it's simple to just draw this out separate from this drawing. You could just draw the triangle to further simplify things. So let's go ahead and do that. So here it is. It's always better to simplify into triangles. In this case, we know what the right angle is going to be located because that maximizes the moment. We have this angle theta 30 degrees, which was given, as well as this length 20 meters. So one thing to keep in mind is, look at this image of the crane. We see that the point O is about 1.5 meters above the floor in this case, or where point A is. So realistically speaking, this continues on to point A here, and so we need to determine an additional amount of length in this case. So we need to determine how much is this distance, and then we need to determine how much is this small little distance. And once you add them up, you get what we're trying to solve for, which is x in this case. And so this is where it's nothing more than trig doing certain steps to get the appropriate dimensions. So we see for this big triangle here that this side is basically going to be equal. Let me go ahead and write it over here. So this side is equal to, if we get cosine 30 degrees, cosine is equal to adjacent, which is 20 millimeters, over that hypotenuse. In this case, let's call it x prime. So x prime. So we have cosine 30 is equal to adjacent over hypotenuse. And we could go ahead and just algebraically manipulate this to solve for x prime. So x prime ends up being 23.09 meters. And you see we just multiplied x prime on both sides of this equation, then divided by cosine 30. So x prime is equal to 20 meters divided by cosine 30, which is 23.09. So we have x prime here, but what about this one? Let's call this one x double prime. What is x double prime? So first off, we see that this is a 30, 60, 90 triangle, right? We have 9 degrees here. We have 30. All three angles of a triangle is equal to 180 degrees. So this one must be 60 degrees, which means that this triangle has the same angle, this smaller triangle. So it's also 60 degrees. And we do have this length, which is 1.5 meters, which was given in the problem statement here, 1.5 meters. So given that we have an angle, in this case we could use tangent 60 degrees. So tangent 60 degrees is equal to opposite over adjacent, in this case x double prime. So of course some algebraic manipulation, x double prime is equal to 0.87 meters. So now finally our full distance x is basically the addition of these two. So it'll be this x double prime as well as x prime. So we just add them up, and finally our distance x, which maximizes this moment, is 23.96 meters. So when you're first initially solving these problems, there may be a lot of information, but just take it one step at a time. Look at ways to simplify, whether it's drawing triangles and getting rid of all the clutter, so it basically makes you see what information you have and what information you have to work with to be able to solve any particular unknowns. In this case, we we were asked to solve the distance, which maximizes the moment, but that basically implicitly stated that this angle had to be 90 degrees because that's the only way to maximize the moment. So this force has to be perpendicular to this distance here to point O to maximize that moment. So sometimes those are the things to look out for. The concepts must be there in order for you to find the first step in the process to solve the solution. And so yeah, this is the second problem here. And the second part to this is, what is that moment? So since we already have that the P is equal to 4 kilonewtons, the perpendicular distance is 20 meters. So in this case, the moment about point O that's caused by the force P is equal to negative 80 kilonewton meters. So in this case, since that force, it basically would be rotating along point O in the clockwise direction. Since I stated my sign convention counterclockwise being positive, the moment along point O is equal to a negative 80 kilonewton meters. Okay, so now for this example, there's a lot of information here. We have a hinge that could rotate about this point, and we have couple moments applied. We have this 150 pounds and this one, each one is equal and opposite, and then we have another couple moment, which is the F. The force here, one is negative force because it's the opposite direction of the other one, F force. So the problem statement is, determine the magnitude of the couple force F so that the resultant couple moment on the crank is 0. In other words, we want no rotation for this hinge here. So the resultant of all the moments must be equal to 0. So the sum of moments is equal to 0. My sign convention is counterclockwise is equal to positive, and they're going to be respect to this hinge, the point at this hinge here. This is where the moment is with respect to that point. So now As you can see, there's a lot of information here. We have lots of angles. Each angle of all the forces, you see this one's 30 degrees with respect to the horizontal, the other one's 30 with respect to the vertical, and so forth. This object itself has a 45-degree angle on both sides, and we have the dimensions, the lengths, 5 inches here, 4 inches here, where the forces are located. Now, this is where you could go force by force, and break it up to its x and y component, because keep in mind, um, previously in previous examples, sometimes only one component caused the force, but in certain instances such as this specific case, you will have a moment being caused by the x component as well as the y component of every force. So just keep that in mind, that when it comes to force components, just because it doesn't necessarily mean that only one of the components will cause a force. Sometimes both of the force components cause a moment. So just be careful with that. So let's go ahead and analyze the first force, being the 150 pounds of force, with and that has a 30-degree angle with respect to the horizontal axis. So the thing is, split to its x and y components. So we have the y component going downward here and the x being this portion. So it's nothing more than trig to solve for the component. So remember, keep in mind, whenever you're doing problems, if it's simpler for you to draw each individual force out with respect to that point where it is going to hinge about, um, then more power to you. Sometimes it's a lot better because there's so much information, you start getting confused, it gets all cluttered, so it's always best to draw it separately. But in this case, I'll do a little bit faster here. So the sum of moments is equal to 0. Let's go with um, the first force. So for the first force, we have a 150-pound force, and I'm basically getting the x component of that force, so it's cosine 30 times the distance that's perpendicular to that force, which is 10 inches times sine of 45 degrees. Now let me go ahead and draw this out just so there won't be any confusion as to how I got this. So, as I stated previously, sometimes it's better to redraw it, and sometimes you could draw just right triangles, which simplify the problem. So here, this is where that force is being applied, 150-pound force, and it's 30 degrees here. So we have from the hinge point, we have 5 inches and 5 inches. So I know the total length here of this hypotenuse of this right triangle that I decided to draw is 10 inches. And we were also given the angle, right? So we have 45 degrees drawn here. So I just went ahead and drew a right triangle. And basically, with respect to the x component of this force, the distance that's perpendicular to that would be this distance here, this side of the triangle. So it's nothing more than sine 45 degrees times 10 inches, which gives us the length of this one. This is where I got 10 inch times sine 45 to give me the distance that's perpendicular with respect to the force of the x component. So keep that in mind. You need to find the distance that's perpendicular with respect to the x component force and the y component force if you do happen to break up the forces into components. So this is for the x portion. Now this moment is going to be causing a counterclockwise rotation along that hinge that we see here. So since this causes a counterclockwise rotation, then it's a positive. Now let's go ahead and look at the y component. So the y component is the component of that force going downward here. And one helpful thing as well is you could continue to draw that line of action of that force. And then we see that the perpendicular distance would be this side of the triangle for the y component of that force. So remember, you could always draw the line of action. Let's go with the x component. You could draw it this way. And we would also be able to see if you draw this line straight, this would be also the perpendicular distance here. And so just keep in mind, you could get creative with it. There's more than one way to solve this problem. It all depends how you want to start it. In this case, I ended up drawing this triangle here, so I'll stick with that. So I decided for the y component, draw the line of action straight down and the perpendicular distance here, which would be this part of the triangle. So in this case, for the perpendicular distance with respect to the y component of this force would be the 10" times cosine 45 degrees. And this y component would also be causing a counterclockwise rotation, which will make it a positive number. So let's go ahead and add it to the equation. So just to reiterate, 150 pounds times sine 30, because we're getting the y component, times the perpendicular distance, which is 10 cosine 45 degrees. So this is the moments added up only for one of the forces. Remember, there's still three more forces to go. So let's go ahead. It's the same process. You draw triangles, simplify the problem, see how you could come up with that distance that's perpendicular to the forces with respect to each of its components. Sometimes you will find some problems where it's very conveniently the resultant force is already perpendicular to the distance from which you're already trying to solve. It's already part of the dimension. But in this case, that's not the case, and we had to find those perpendicular distances. So let me go ahead and write it out for all the forces for this equation, the sum of moments. So now we finally get this very long equation for the sum of forces of moments. And of course, all this is equal to 0. And we do have the variable f in this case. So let's go ahead and simplify this a little bit more by multiplying all of these numbers and just factoring out the f and solve. So this is how it looks a little bit more simplified. Once we add all these numbers, it's 1138.31. Take away these constant coefficients along with the force F here. And we just add the F's here together, which gives us 1138.31 take away 5.87f is equal to 0. Then we move the f to the other side and we divide both sides of the equation by 5.87. And that finally leaves us with f being equal to 194 pounds. So this is finally our answer after all that work. So sometimes it could be simple and easy, other times it requires multiple steps to get there. Now, another way that could have been used to solve this same problem is, let's go back to the drawing here. So you know how in this case we decide to split up the components into the x and y component, get the moment each of the component that calls for each of the forces. Another way is to get of each of the components, basically project it, project it to the specified angle such that it will be perpendicular to the lengths that are shown. So in this case, let me draw this out. So this is the length. So from the hinge to this force at the end, we would essentially project at what angle is this perpendicular to that line. Now, the very convenient reason why we would do this is because we already have the lengths. In this case, it'll be the perpendicular length 10 inches from the hinge point to this force that's being projected that's already a right angle with that distance. But the trick with this is finding what that angle is. So it's some geometry, some trig, trying to find what that angle is for each of the forces. And you only project this force onto that path which is already a right angle with this line here. So that's another way that could be a little bit simpler if you have the hang of trig, if you kind of just by visual inspection could identify the angles that are missing to project these forces that are already at a right angle with respect to the dimensions that are seen here. So there's always Sometimes there's more than one way to solve the same problem. One way may be a little bit longer, the other one may be simpler, but it's up to you to decide to see what's more obvious for you. Some people, it may be too difficult to identify, and so you go this longer route, which is perfectly fine. And so this is how you apply the concepts of moments as well as the summation of the resultant moment to be able to find any unknowns in the particular systems. In this specific problem, so it was to solve the force such that there was no moment about that hinge.